What is the amplitude? What's the period? Based off, calculate out the other things off of it too, like what the frequency is and stuff like that. So the first thing we want to know is, so we'll take a look at our first one. We'll take a look at what is our period across here. So what it does is on the bottom of your screen, on your oscilloscope, it's going to tell you what your setting is set at for your horizontal divisions here. And it's going to say how many seconds per division. So for this particular one, it's going to be...
It's on the top.
Oh, let me get rid of that. Thank you. So our seconds per division is going to be our 0.1 milliseconds per division. That's going to be our horizontal division. So what it's saying is that for every one division, that's going to be equal to 0.1. So I'm going to have 0.1, 0.2, 0.3 milliseconds on all the way across. And then when we also have then our subdivisions. And those are going to be, depending on if there's, like, for example, here there's 4 subdivisions on our vertical one. These are a lot larger, so I can show you. So each one of these subdivisions, here we better stick with the horizontal. So for example, we're going to have all our major lines are going to be one division. That's going to be our 0.1 milliseconds. And then within there is going to be our subdivisions of that. So for example, if there's 4 subdivisions, I know that then this is going to be 0.2, 0.4, 0.6, 0.8, and then I'm going to be at my next subdivision, or my next major division. So depending on if I have 4 or 3 lines, typically you're going to either have 4 or 3 subdivisions. If you have 4 subdivisions in there, each one of those are going to be equal to 0.2 of a division. If you have 3 of the subdivisions in there, then each one of those are going to be equal to 0.25 of a division. So let's take a look here. So if we, so here we're going to just say that each one of our divisions is equal to 0.1 milliseconds per division. You're just going to start from where it starts out at 0, and you're going to do one complete cycle. So we know that, here's my one complete cycle. It goes up, goes down, and then at this point it's going to start to repeat itself. So I want to count how many major divisions I have for that one complete cycle. So I'm just going to start here, and I'm going to just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to have 10 divisions, and what I recommend you doing is just doing it using your calculator so you don't make mistakes. Or if you're good with your math and you know that if I take 10 times 0.1, it's going to be equal to my 1 millisecond. But just to get in the habit of doing it, what you want to do is count how many divisions you have. Do that first. Doesn't matter what this is. Just count how many divisions you have plus your subdivisions. So for example, I had 10 divisions, and I'm going to multiply it by my 0.1 milliseconds. Keep it in engineering notation, and I'm going to end up with a total of 1 millisecond. So my period is going to be equal to my 1 millisecond. Okay? Now once I know what my period is, so I know that it takes 1 millisecond to complete one cycle, then I can tell you what my frequency is, and what would be my frequency of that sine wave. What's that? 1 kilohertz. Okay? So I know that my period took 1 millisecond to complete one cycle. I know that my frequency is at 1 kilohertz. And now my next thing is I want to do is I want to measure what my amplitude of it is. That's going to be my vertical. My vertical position. How high does it go? So on this one here, now my vertical divisions are going to be 2 volts per division. So again, I'm just going to start out, and I want to go up to my peak value. I'm just going to count how many major divisions I have. I got 1, 2, 3. So then I can just go and I can take 3 times my 2 for my divisions, and I'm going to get 6 volts. And what's my units for this one? 6 volts what? Peak. Okay, and what would be my peak to peak? 12. Okay, so when I'm looking at the oscilloscope, I can either measure myself my voltage peak, or I can go from here to here and I can measure my voltage peak to peak. Or I can just measure my voltage peak and then divide it by times it by 2. Thank you. Okay. I know that and then on this one here, I'm going to assume that my DC reference is going to be right here at 0 volts DC. It's right now on that 0 volts DC. We're assuming that there's no DC offset on there. But if there was a DC offset on my oscilloscope, on my digital oscilloscope, what I'm going to see is an arrow over here, and it's going to say channel 1. And it's going to point to where my 0 volts DC is at. If I were to have a DC offset in it, depending on if it's a positive or a negative DC reference, my channel 1 might have said that my 0 volts DC was right here. Okay? So would that give me a positive DC reference or a negative DC reference?
Negative.
So here's my 0 volts DC right here, and it's going to tell me that channel 1 is pointing right here. Here's my 0 volts DC. So is my sine wave riding a little bit higher or a little bit lower than my 0 volts? It's a little higher, so that would give me a positive, and I'd actually really be at, just because we know that this is where it's riding on, we know that half my voltage peak, so it's my half this voltage peak, I'd actually have a positive 2 volts DC reference there. If I wanted to calculate out that DC reference, and I think I put that on my cheat sheet here too, because that's a good thing to know. I put that in there, didn't I? It is in the book there though, so let's take a look at that real quick, because that's a good thing to know on how to calculate that out. That is on superimpose Vmax, Vmin. It tells you how to calculate your Vmax and Vmin, but not your DC. Because what happens is that, so we'll just use this one here. We'll say that this is my 0 volts DC. This doesn't change this. This is still going to be 6 volts peak and 12 volts peak to peak. It's just, where is it referencing it to? So, let's see, maybe, yeah, that'll be okay. So what I want to do is, I know that this is my 0 volts here. So what I want to do is calculate out what my Vmax is. So basically what I'm going to do is I'm going to just count how many divisions I have from my 0 to figure out what my Vmax is. So from 0 I'm going to have 1, 2, 3, 4 divisions. So I know that my Vmax
what's the current on
is equal to a positive 8 volts. I know that I already knew that I had a 12 volts peak to peak or 6 volts peak to peak, and I know that half my voltage peak is always going to be riding on that DC reference. So I know that my Vmax is at a positive 8 volts. So if I want to figure out what my voltage DC is, all I have to do is I just have to take my Vmax and minus my voltage peak from it, and that'll give me my voltage DC from it. So if I take my Vmax of a positive 8 volts, make sure you use the polarities, and subtract it from my voltage peak with no polarities, that'll give me my voltage DC. So what would I get for a voltage DC then if I plug that into the formula? I'd get my plus 2 volts. Okay? So a lot of times you need to know where that DC reference is. Okay? So what you're going to do is first of all just calculate out what your Vmax is. You know you're going to know where your zero is. Your oscilloscope is going to tell you where your zero is. Calculate out what your Vmin is, your Vmax is. Calculate out what your peak to peak is, because you can't really calculate out your peak because you don't know where your DC reference is. So you're going to calculate out your peak to peak. So you're going to go 1, 2, 3, 4, 5, 6 times my 2 volts. I've given you my 12 volts peak to peak. So calculate out your 12 volts peak to peak, divide by 2, get your 6 volts peak, and then just subtract that from your Vmin, and that'll tell you where your DC reference is. But because there's a lot of times you don't really know where that DC reference is. This might be, 2.2 volts or something really hard to see. But if we calculate it all out, we can exactly measure what our DC reference is. Okay? This will probably be on the quiz. I think that might even be on next week's quiz there, so should know how to do that. And it's just basically the formula for Vmax is just manipulating it around. Okay? So we can calculate out what our DC reference is. So on this particular one, our DC reference was going to be, since we moved it, it's going to be a positive 2 volts DC. It's 6 volts peak, 12 volts peak to peak. It's 1 millisecond for the period, then it's going to be 1 kilohertz. Okay, so just by looking at the screen, we can analyze everything we need. Let's find it. Alright, I was hoping I had one with a subdivision in there, but that's okay. Alright, so let's take a look at our second one here. But what would I end up for measuring for, so what would be my period on this one? So my second one, what would be my period for that one? 8 milliseconds. So I got my starting of my cycle here, goes up, goes down, and then it starts to repeat itself at that point. So my period is going to be 8 milliseconds. Okay? And then my frequency of this one is going to be what? Is it going to be more or less? Am I going to have a higher frequency or smaller frequency or a larger frequency than the one previous? It's going to be a lot smaller. It's going to be 8 times smaller. So what do I get for our frequency? 125 hertz. Okay, everyone catch on to that then? Pretty straightforward. Okay? Alright, then what is going to be, what's my amplitude then? What's my voltage peak to peak on this one, or my voltage peak? What would be my voltage peak on this one?
0.4 volts.
0.4 volts. Or the same as saying 400 millivolts peak. And what's my voltage peak to peak then?
800 millivolts.
800 millivolts multiplied by 2. Okay? Then we're assuming DC reference is going to be right there. Okay, so that's how we interpret the signal looking at the screen there. Now, one thing nice about the digital is that because we can go to our, oh, what do they call it? Our measure button. We go to our measure button on our oscilloscope. I can even bring it up and I'll show you what we got. But on my measured one, it'll tell me what my Vmax is. It'll tell me what my Vmin is. It'll tell me what my period is. It'll tell me what my frequency is. It'll tell me what my voltage peak is, my peak to peak. So I can have it all display everything on here. And it works very good for very basic sine waves and square waves and stuff like that. As long as the waveform is very of a basic waveform. But for example, but right now when I'm at my other job is what we're getting is what we call we're getting some severe common mode going through our rectifier. And what I'm trying to do is analyze, figuring out where that common mode is coming from. Is it coming from our servo drives, or is it coming from our, some out of our PC, or where is it coming from? But when I display it on my oscilloscope, my signals are looking like this. Here's my, I know that I'm going to have I'm sitting on a plus 12 volts DC reference. And all of a sudden it'll be going along just fine. And then all of a sudden I get these, then all of a sudden it sits there and stays at my 12 volts, nice and clean what I want. I want a nice clean 12 volts DC. And all of a sudden the thing just starts, and it's very repetitive.
It's alive.
It's alive, yeah. And so I'm getting this common, what we call common mode. It's noise. I know it's coming from my servo drive, but now I'm trying to figure out how to eliminate it. These voltage spikes here, I'm getting almost as 50 volts peak to peak, so it's heating up our device under test way more than what I really want. I want just a nice constant 12 volts, okay? So what I'm doing is I'm analyzing the signal. Now when the oscilloscope looks at it, the oscilloscope is trying to figure out what the period is. Well, the period, because here's the beginning of my cycle, and it sees this, then it goes, and then it repeats itself at this point. So what it thinks is the frequency is from here to here. So that's what it thinks the time is, the period is there. Well, what I'm looking at is what I want to know is what this frequency is of this spot here is. This is the only thing I'm concerned with. So I can't use the measured values that my oscilloscope tells me. I have to calculate it out. So what I do is I zoom in on just one of these areas, I spread them all out so that I'm getting about 10 divisions on there, and then I'm calculating on what this frequency of this is. And I know that this frequency here is about 2.5 kilohertz. It happens to be set up the same frequency as what I'm switching my servo drives. So now I definitely know that this is coming from my servo drives because that's exactly what I have my switching mode going on my servo drive as I do what's here. But I couldn't rely on the oscilloscope to tell me what this frequency was. I had to manually calculate it out, doing it this way. So don't get too careful. Don't rely on what the oscilloscope does. The oscilloscope is just going to make an assumptions. This thing here, this thought this was one complete cycle. But what I really wanted to know was what the frequency of this was, not the frequency of what that was. So, for example, if I can bring up the oscilloscope here. So again, everything that we're doing right now, everything is nice and basic. Everything works nice. The labs have been all proven out. They all work and stuff. But remember, when you get out on the job, every day is going to be a bad lab day for you. And so we have to do things, we can't do everything the easy way. Sometimes we have to manually calculate out things. So don't get too reliant on the measure. So if I go and this is that, other than it being a 4-channel, this is the exact oscilloscopes that we have in our other lab bench, and this is just going to multi-sim. But I can go ahead and I'll run this one here. So I'm going to simulate the circuit. So here I have a function generator going into a DC source. So I'm superimposing an AC signal onto across a 1K ohm resistor there.
Let me change this up here. That piece.
So there's a couple different things. Here's that oscillation. I don't know if you can see that. It's pretty hard to see, but I don't know if you can see those lines is all kind of scattered around, all jumped around all over the place. There's a couple different arrows. Here's my one on the right-hand side. This is my trigger. And then the one on the left-hand side, this is the one that I was telling you. It's going to tell you it's going to be channel 1, and that's where the zero reference is. Okay? So it's trying to trigger, but it's scattered all over. So the first thing I'd want to do is I want to go to my trigger menu. And I want to look.
Should be on channel 1. That should be okay. Shorten up the time here. Just change the type too, or?
There we go. I think the frequency of it. Still kind of very slow, but multi-sim doesn't simulate everything just proper. But now there's my trigger level. It's triggering at about approximately right here. And then what I have is another arrow right here. So this arrow here is indicating where the starting of my cycle is. And then here's my trigger level. So right where those two intersect, that's where that signal is going to start to trigger. That's right where it's starting to draw off that sine wave. It's right at that point there. Right where those two crosshairs are. That's the beginning of my signal. If I want to, kind of like when we were doing it on the other thing, if I want to, I can move that position over. And I can move it over to the very far left. And now, what I did is I just moved this over to here. My trigger level stayed right here. Here's my crosshairs, and now I'm starting to draw right at the beginning of the waveforms there. So we can kind of move around with the position of where it's at. All right, so you wanted to have one complete cycle in there, so I have one complete cycle. I know I can't go any more than that because I'm a little bit over 5 divisions there. So I'm going to go and I'm going to click on. Maybe I can go. Can't go any more than that. But what if I can do now, once I go to measure, I can select on what I want it to do. So I can tell, channel 1, that's the channel I'm on. I can go and click on the source channel 1 and then what type I want, and I click on the button. So there it'll tell me what the frequency is, and it's telling me that it's at 1 kilohertz. Having a hard time picking up on it. It'll tell me what the period is.
Why this thing's having a hard time triggering out?
Should be triggering a little bit better than that. But it can tell me what the period is. I can click on it. It'll tell me the mean. The mean is actually the same as my DC reference. So it's telling me, if you see it flashing once in a while, it's telling me that I got a negative 25 volts DC. And that's exactly what I have on there is my DC reference. So it'll tell me what my mean is, my DC reference. Tell me what my peak to peak is. So it's about 39.8 volts it's saying. It'll calculate out the RMS value for me, the Vmin, the Vmax. It'll tell me what the rise time is. So if we're working with pulses, we can look at the rise time, the fall time, the positive width, the negative width, and then back to none. So it'll tell me everything about that waveform that I want. But again, don't rely on it every time, depending on what your signal is. All right, so it's just your volts per division and then your seconds per division. All right, any questions on any of those? I'm measuring the signals. Yeah.
Just want the 4 things, time, frequency.
Yeah, and your phase is just going to be, you can just treat it as 0 volts. Or 0 degrees, I mean. Yep. Yep, so you always should know about the four things about a waveform. You know, what type of waveform is it? This is a sine wave or a square wave, depending on what it is. What the amplitude is, what the DC reference is. You know, on these ones you can just assume that it's, 0 volts on the other ones. What the time is, which is, is the same as the period. And then the phase, you can just assume that it's at 0 degrees. We'll talk more about the phase when we get into RC circuits. Let's see, since we all are going to have one of those on the quiz, let's just say that, let's say that my DC reference, so this is going to be our channel 1, so that's going to be our channel 1 reference, that's going to be our 0 volts DC reference. What would be my DC offset on that? Calculate out what your DC offset would be using what we just did on with the formula. And I know that's going to be on one of our quizzes there on how to calculate out it, looking at the sine wave and determining what the DC reference is. So see if you can do that on your own here first. Calculate out what the DC reference would be if my 0 volts reference is right where it says channel 1. This is a good one here's one I'll kind of help you out here to begin with. So we know that this is 0 volts right here, right? So we know that my Vmax is going to be going up to here. So here's a good example of it. So if I draw the line across here, typically what we can do is we can just take our position and we can move it over so I can get in there. So you're going to start out your 0, then you're going to count how many major divisions you have. So you're going to start out here, I'm going to go 1, 2, then count how many subdivisions I have. So I got 1, 2, then I got 0.2, 0.4, because each one of these subdivisions are going to be equal to 0.2. So what I would do is I would put in my 2.4 times in how many volts per division I have. So for example, the 1 volt times 1 would give me my Vmax equal my 2.4 volts. That would be what my Vmax is. Okay? So each subdivision would be equal to 0.2, so that's I just count them as 2, then 2, and then 0.2, 0.4. And then I just multiply it by what the volts per division is. So what would be my DC offset if I had my 0 point right here? Remember how to calculate out the voltage DC reference? Or remember how to calculate that out? Negative 1 volts DC. Yep. So I got my Vmax is 2.14 volts. What was my what's my peak to peak voltage?
3.4. Well, 6.8.
6.8. Yep. Then half of that was my 3.4. So then I'm just going to take my Vmax minus my voltage peak. So I'm going to just take my 2.4 volts, positive 2.4 volts, and subtract my 3.4 volts, and I get negative 1 volts DC. All right. And you guys can calculate everything else out here, stuff like that. So, yeah, know about the 5 things about your waveform.
Why would somebody calculate that as instead of 2.4 be like 2.5.
Well, you could, I mean, again,
I mean, how are you gonna calculate that on the test if it's in between like that? I mean,
well, it's not gonna be, what I do is I make sure that, you know, when I do it on the test, I have it so that it's, you know, it's definitely on the line.
okay.
Yeah, yeah, it's definitely on the line. But yeah, you know, if you said, because remember I said that the accuracy of us measuring off of an oscilloscope isn't critical. What's critical is us looking at the waveform and knowing that we got the approximate voltage. So realistically, you know, we really can only get down because each subdivision is only equal to 0.2, right?
Yeah.
So the largest and bottom number that we can really measure is 2 point, let's say for example, 2.4. But you know, if we're halfway in between, then we could really go, 2.45. So you're really only going to be 2 decimal places. That is going to be the most accurate you're ever going to measure on an oscilloscope. But again, not so critical, but is the waveform there? Yeah. Yeah. But yeah, I always do make sure that it's always kind of right on the line, so it's definite. You can definitely see it, or if not, if you're within close and calculated everything else out, ain't gonna be too worried about that. All right. Let's try going over our pulse widths real quick, and then we don't have to come back in here tomorrow. I'm gonna have you read about the alternators and motors and stuff like that. We're not gonna. We got so much of the basic stuff that we don't need to start talking about motors. And the motors they're talking about are your typical motors for running fans or blowers and stuff like that. Motors that we're going to be working with are kind of the asynchronous type of motors, stepper motors, servo motors, and stuff like that. And they get to be a little bit more on the complexity side. So we'll let Tom take care of that in automation controls. Here. What's that? Yeah. So we're going to be on page 358. Then we'll get going into lab, and you'll have a lot of questions in lab, and I'll be going up on the board a lot, telling you how to hook up things. And the labs are definitely going to get on a little bit more on the complexity side. They're really actually going to have you figure out what the bandwidth of an oscilloscope is and stuff like that. So it gets kind of flux side. All right, so on page 359, it's showing so what we're looking at is the pulse waveform. So this is going to be one of the more common type waveforms that you're going to be using. And basically it's just going to look like a square wave. Okay. This is how we transmit bits of information. Okay. So if I have it very repetitive, I got something off just as long as I do on, off, on, off, on. This is going up to, typically our voltages are plus 5 volts, and then it goes down to 0 volts. Okay. If I see something very repetitive going into an IC or into my data acquisition or something like that, this is what would be considered our clock pulse. Okay. This is what's synchronizing all our data going through. Then we have this clock pulse that's always constantly going into our chip. It's going to be what shifts all our data. It's going to be what knows when to start to handle our data coming in. So the data coming in might be from a transmitted line from our PC coming out of our serial port. And that data might look something more like this. And it might be off for a while. Then it's going to be on, you know, and then off, and then back on again, you know. And so the data that we're seeing is going to be something more like this. It's all going to be, all this is going to be synchronized to the same clock pulse. You know, this same clock pulse could be at 1 kilohertz, 100 kilohertz, it could be at anything. And what it's going to do is it's going to synchronize all our signals. And this is going to be our bits of data that's coming through. You know, so if we have, you know, 4 bits of data, you know, so from here to here, you know, we might have 4 bits of data coming in here. So what's 4 bits equal to? 1 byte. So we might have 1 byte of information, and that's going to be an ASCII. That's going to be in our binary format. It's going to be, so for example, every time it goes high, it's going to be a 1, and then it's going to be a 0, 1, 0. Okay. Right, 1. Oop, this is 1, 2. There. So what I have is I have a, you know, and then this byte of information is going to represent something. You know, it could be representing an ASCII character. It could represent a number. You know, it might be a number if it was, you know, a number. Let's see, what would that? God, I figured that out. Whatever that number would be. Let's just say it would equal to
15.
15. Is that what it is?
Yes.
Thank you. So it'll be, oh yeah, because it'd be just 1 less. So that might equal a value of 15. So we might be sitting at, you know, going into another microcontroller or something like that, and we want to tell it to set it at a 15, a level of 15 or something, some kind of data and stuff. So this data is going to be coming in and it's going to be synchronized with our clock pulse. But we have to have this clock pulse to know when all this data is coming into our chip, our microcontroller, or our PC, or whatever it is. When we draw up these waveforms look very symmetrical. They look very nice and clean and stuff like that. But when we really actually get down to it, we actually end up with rises and slopes, and like Jeremiah was talking about, that he was seeing a lot of ringing. So let's take a look at it. So this is one, you know, this is probably one of the more common AC signals that you're going to be working with. Is the data and stuff, you know, sending data back and forth. So let's kind of zoom in on. So what we got is we're going to have I'm going to just zoom in on one pulse width. So what I'm saying, it's going to go low, then it's going to go high. So that's what it actually looks like. And if I can do that, you know, if I look on in the oscilloscope, and if I have my time. If I have my time very long length of time, it just looks like a nice perfect square wave. But if I really zoom in on my time, I really narrow down my time and make it really quick, then I can see that I actually have a rise and a fall on this same signal. So what we do is we like to know what is that. This is what we call our propagation delay. Just like I said, you know, we have this clock pulse that's coming in. And then it's also at the same time synchronizing our data that's coming in. Well, on these clock pulses we have, there's a range here. We're going to go 10% and 90% of our maximum value. So, you know, if it's a 5 volt signal, it'd be 90% down and 10% above. Those are going to be two spots that we mark on our rise time. And then what we do is we drew a line down there. We could actually measure the amount of time that it took for that signal to rise. And that's if we're doing something with very large amounts of data or transferring stuff very quickly. If this time takes way too long, we could literally actually miss a signal, or we could have so much propagation delay because by the time I get through thousands of digital circuits, all this stuff adds up because it's not going to turn on instantaneous. It doesn't go from 0 volts to a plus 5 volts instantaneous. It takes a certain amount of time for it to transition from 0 volts to plus 5 volts. And that little time there is our rise time. And we have the same thing here. 90 volts, or 90% here, and 10% here. And then we have that, and that's going to be our, so here's our rise time, and then this is our, how much it took for our fall time. Okay? Our time width, you know, how long does it actually take? How long is that pulse width on for? Is going to be from our 50% mark. So that's going to be from here to here. That's going to be our time width. Okay. How long is that pulse on there for? You know, because we want to know how long is that time width. That's our pulse. That's going to be our pulse width. We're going to have a negative 1 pulse, or we're going to have a positive 1 pulse. Doesn't matter what it is. Calculate everything else the same way. Okay, so this is going to be actually our pulse width, or our time width, of what the actual pulse is. That's at 50% of our waveform, of where that rise time and the fall time. And this is where those cursors come in handy. So when I was talking about the cursors on the oscilloscope, so what I could do, if I wanted to know exactly what my time width was, I can put my cursors on, and since I'm talking about time width, I'm talking about time, so is that a horizontal position or a vertical position? So I'm talking time on an oscilloscope. Is that horizontal or vertical?
Horizontal.
Horizontal. Okay, so what I can do is I can use my cursors in the horizontal position. And so I'm going to just simulate, if I had this on my oscilloscope and I want to measure my time width, I can put my cursors and I can move my cursors over. And what it's going to do is as I move my cursors over, there's going to be little crosshairs on here. Well, I know that I want to be at 50% of my amplitude. Well, I know I'm going from 0 to 5 volts, so I know that I want to be at a positive 2.5 volts. Okay? So my cursor will actually automatically follow this rise time, and this cursor will kind of follow up. And wherever this line is at, right where those crosshairs are, these crosshairs are going to follow this rise time. It's automatically going to follow that. And when it gets over on the right-hand side of my screen, this cursor is actually going to tell me where this vertical position is. And it's going to tell me that it's at 2.5 volts. At that point, then I know that I'm at 50% of my rise time. Then so this is going to be our cursor 1. And then I'm going to do the same thing with cursor 2. I'm going to bring it over. And as I bring it over, it's going to draw the crosshairs, and it's going to tell me that it's at a positive 2.5 volts. And this is going to be my cursor 2. And then what I can do then is I can take a look, and over on the right-hand side, it's already going to calculate it out for me, but it's going to tell me what my delta t is, my change in time between cursor 1 and cursor 2. And it's going to give me some number. It might say 5 nanoseconds. Oh, that's way too much for a time, but let's see what I said. It might say, oh no, yeah. So let's just say it's going to be, we'll say 100 microseconds. Okay? So then I automatically know then, it's automatically going to tell me that my time width on this particular waveform is at 100 microseconds. I can use my cursors the same way to figure out what my rise time and my fall time is. If I know that I need 10%, I know that I need to be at about 0.5 to, what's 90% of 4.5? 4.5? I can do the same thing for my rise time then too. I can bring both my cursors over, line up so I'm at 10% and 90%, and then it'll calculate out what my rise time was. And then that would be my delta t. And that would probably be something around the 5 nanoseconds or something, depending on where, what frequency you're at. Okay, a very short amount of time. And so I can calculate out what my rise time is, what my fall time is. Then I would know what my propagation delay is. Let's see. Rest of it you're not. The rest of it you can kind of figure out on your own. But there's one other thing that Jeremiah brought up that you want to kind of go over. again, the inconsistency of, you know, what a true signal looks like and what a real signal looks like. When you're looking at these signals, this makes it nice and easy. It looks really simple for what I just did on the board, but when you really get into it and you start looking at it, what you're really going to see is something like this. That square wave, when I get zoomed in on it especially, it's going to look something like this. It's going to go. And then when it goes down, then it's going to do the same thing. And so you're going to get what we call ringing. The transition between this thing going from 0 to 5, it's going to overshoot it. Then it's going to try compensating for it inside the circuitry, inside the oscillator and the function generator. Then it's going to try to compensate for it. Then it's going to undershoot it, overshoot it, undershoot it, and then finally it stabilizes out. Well, sometimes that stabilization doesn't even happen until it gets to the end of the thing there. All of a sudden it goes like this, and then all of a sudden it drops down. So then it's really hard to know where the heck is even my 5 volts at. You know, I don't even have a nice straight line. And so you're going to see this, and this is what we call our ringing. And you'll see that when you go ahead and do your measurements on your on the function generators. Now we got a whole bunch of new function generators, so I'm going to be really curious to see what our ringing was. We had some old analog function generators, the ones that I kind of pulled up, that black one. Not this digital one, but this one right here, this old. This thing is back from the 1970s. When you were here. When I was here. Yep, exactly. I think I even got pictures of me working on one of these.
Is that installed?
So that one there from 1970s actually has less ringing than what these brand new digital ones do. These analog ones are about the best. I keep on reverting back to them. But these things have finally seen their life expectancy. It was kind of funny. We never had one of these things go bad for maybe 1 or 2 here and there. But last year, all of a sudden these things started dropping out like flies. And it was probably because one of the capacitors started failing on it. But it was funny though, they all kind of expired at about the same time. Something started failing on them, and these things started dropping out like flies last year. I was kind of bummed out because those things are the best function generators, even though they're old and antique things. They're the best function generators we've got. But we picked up a bunch of new ones, so I'm going to be really curious to see what type of ringing we got. But the guys that were using this one, geez, that ringing was so bad, I even had a hard time figuring out where in the heck, where the 5 volts was. But the guys that were using the old antique one, boy, you could just definitely see where the 5 volts, that ringing stopped pretty quick and stuff, and you had plenty of area to kind of do your measurements.
So are we gonna fix those old ones, or?
Alright. I probably will eventually. I'll kind of hang on to it because we got a whole bunch of schematics for them and stuff. I got all the data for them. Have all the troubleshooting guys. We're going to use that for our tech doc class for troubleshooting and stuff like that. So, alright, make sure you read the rest of the chapter. Read about the motors. That's good information. The phases, we'll talk more about phase shifts and stuff like that when we get into RC circuits.
Oh, you need help?
Definitely read up on the oscilloscope. I understand how to use the oscilloscope. Yeah. Well, we'll get there when we're going out here tomorrow.